Good morning, everyone, and welcome to today's webinar from Embeddle, the many avatars of knowledge distillation. My name is Devdutt Dubashi. I'm co-founder of Embeddle and chief scientist, and I also am a professor in the data science and AI division at Chalmers University. And with me today, joining me is Willem Tranheden, who is a deep learning researcher here at Embeddle. So the title of the webinar today is The Many Avatars of Knowledge Distillation. Now, avatar is a word from Hindu mythology where the Hindu gods appeared in many different shapes and sizes in many different stories, and they kept coming in one form or the other. And this is exactly what we're going to do today with knowledge distillation. So we are going to see that knowledge distillation reappears in many different forms and guises and helps efficient deep learning in many different ways. So that's going to be the story we're going to talk about today. And please, if you have get ready with your questions and comments and put them in the chat. We'll pick them up for discussion later on. And then, it will be really great to have active discussion at the end of the presentation. So with that, let's go. So I'm going to start with a very general introduction to what knowledge distillation is, what was the original formulation, some of the state of the art in the area, and many different ways in which it appears now in today's state of the art, with a lot of developments after the original suggestion. And then we're going to move over to show how great it is. So we are going to make the case that it's a very important part of the toolkit of people working in efficient deep learning, and that it can be used very effectively with other parts of the toolkit in compression. And we're going to showcase it with a couple of examples with vision transformers for NVIDIA GPUs and for MobileNet 2 for ARM CPUs. And if you stick around to the end, you will see that you can get some very remarkable improvements. You can get up to 5-6 times faster. And there are also other people recently who have shown that with other well-known standard models, you can get sometimes even 50 times improvement in performance. So pretty remarkable improvements with a very basic idea, a very nice, beautiful, simple idea that you can then leverage very efficiently. So that's going to be the story for today. So what's knowledge distillation? So it's a very, so let's go back one slide. So it's a very nice, simple idea. The basic idea is you have what is called a teacher model, which you can think of it as a very large, big neural network. But if you want to do efficient deep learning, you want to do it with a small, agile student network that can run with much reduced resources on much reduced compute in a small device sitting somewhere in your home application. And the idea is that you should transfer the knowledge that this big neural network has in a way that can be used in the smaller model. So you want to transfer the knowledge from the teacher model to the student model. And that's the basic intuitive idea of knowledge distillation. And by the way, I can recommend a recent survey that appeared in the International Journal of Computer Vision on knowledge distillation. It's a few years old, but it has the basic idea and many of the improvements up to that date. And then we have some more additional things that we are going to talk about today as well. So how exactly can we transfer this knowledge from a teacher model to the student model? That's the basic question, right? So how exactly, this basic intuition is fine, but how exactly are we going to achieve this knowledge transfer? And this is the original proposal. So the original proposal was that you have the teacher network with its logits at the final output layer, which is the final probability distribution that you will use in your tasks, such as classification. And you have the student network, which has the same output layer, or where it has its output layer. And the idea is that you should use these, you should match these two output layers between the teacher and the student. And that way you're going to transfer the knowledge that the teacher has learned into the student. So if you think about this from a machine learning standpoint, with the view, a machine learning hat on, what this amounts to is to say that you're going to transfer the representations. So it's going to be distilling knowledge via transferring the knowledge in representations. So what we assume is that the teacher, since it's a very good model to solve a particular problem, has developed a representation of data that is extremely powerful, flexible, efficient, etc. And that is the representation that we would like to transfer to the student. So this is the original proposal. You use match the output layers of the two networks. And of course, the specific way in which you're going to do that is you're going to match the distribution. So these are probability distributions at the output. And so you can match these probability distributions with a cross entropy or any such loss function that matches probability distributions. You can match those in the loss function. And so the original idea is that when you train the student network, you do it with a combination of two terms. One term is the usual training loss with the real training data. And the other is this loss based on the representations, matching the representations between the teacher and student. And that's the second term. And you combine the two terms with a suitable tuning parameter that weighs the loss between these two terms. And you train the student with this process. So part of the loss comes from the training data, and part of the loss comes from matching the representations. That was the original proposal which originated in this seminal paper. And you can see some famous names, Hinton, Vinyals, and Jeff Dean. Distilling the knowledge in the neural network. This paper appeared in the NeurIPS Deep Learning and Representation Learning Workshop from 2015. So you see that the context of the workshop is exactly representation learning, and that's how it was presented. So this paper is, today one of probably, an extremely important paper that much of the rest work since has flown out of, but as far as I know, it was never actually published in any other forum apart from this workshop. So it's quite interesting. Normally, the workshop is a place where you present some preliminary results, and then you present the final version of the paper in a conference or a journal, etc. But this paper never got published anywhere else. It's still only available as this workshop presentation. Well, that might be because these people went on to do lots of other work. So it's one of those rare cases where there's a very extremely important paper that has only a workshop publication. So this is the basic idea. Now, if you think about this, I mean, it's a very beautiful and simple idea, which we should all digest. I mean, it says that the student can be trained with a combination of the normal training loss and matching the representations. And you can also see that there are, when you think about it like this, now it opens up a world of other possibilities. I mean, you can maybe get rid of the training loss and train it just on the representations. That's possible. And why should we simply do it on the output layer? Maybe we can match representations in other places as well. And so that was, it's opened the floodgates to a lot of research stemming from different ways in which we can think about it using this basic idea. So here is one way to do that is, let's say that we want to transfer the knowledge and the representations from some intermediate layer. So we can have a distillation loss between intermediate representations. And this is an extremely powerful idea, right? This means you can use it, you can use it to train the whole model, but you can perhaps use it to train a particular layer. You can use the distillation loss as a way to see how you should build particular layers in between. So you can also do it across layers. Now, if you do it across layers, there is a certain issue that arises, in particular, with intermediate layers. So here's a paper that appeared soon after the original ones called FitNets. And you see another very famous author there, Yoshua Bengio, and a couple of others in their group. And so they observed that if you want to do this variant where you transfer knowledge at an intermediate layer, you're going to come up against the issue that the architectures can be very heterogeneous. So this is the student architecture, which is deep and fat, and the student network may be not so deep, and maybe extremely skinny. So then the intermediate layer here is not going to match the size of the intermediate layer in the teacher network. So how do you transfer the representations in this wide intermediate layer to representation in this small, in this thin intermediate layer in the student? So the idea they suggested was that you add on top of this thin layer a regressor module that simply matches and does the job of matching the size of the representation at the output. And then you're going to train this combination like this to match the output here. So this was, again, a pretty simple idea that extends the original proposal. You're using the same distillation idea to train an intermediate layer by adding this regressor module. And they also, in the paper, say you can combine it with, at the end, doing the final distillation step as you had in the original paper as well. So you can combine it in many different ways. You can do only the intermediate distillation, or you can combine that with doing intermediate layer training together with the final layer distillation, etc. So when you see it, put it like this, you can see that the possibilities are immense. You can make many different combinations of using this very simple idea of distillation in many different combinations. So this paper appeared in iClear just a few years after the original paper by Hinton, Onyals, and Jeff Dean. And now we can look at a variant of distillation from just a couple of years ago now. This is a paper from ICCB in 2019. And this is a take on distillation that goes beyond just these features that you have in the examples we just saw. So here, the idea is you're going to do knowledge distillations by looking at preserving similarities of features. So what's the idea? Let's look at it in a little more detail. So the figure on the left shows that similarities are usually measured by getting a matrix of similarities like this. So if you get the information of similarities in the form of a matrix of this kind, a similarity matrix, we can use that to do the distillation. That's the idea that these people took up. So again, the basic idea summarized on this slide. So you have on the top the teacher network, and at the bottom you have the student network, and you see that they can have, in general, different architectures. They have a similar, maybe a backbone structure, which might be similar. You have matching blocks, but each of the layers are very different. So this one perhaps is a wider layer, and there are many of them. Here, maybe there's a thinner layer and a fewer of them. So this is the student network, which is much smaller, and you have a teacher network on top, which is much bigger. But now the idea of similarity distillation. So what's that about? So the basic idea is going to be that you want similar inputs to elicit similar activation patterns, right? So the similarity between inputs should translate into similarity in representations. It's a very key and powerful idea in many areas of machine learning. Let's bring that into distillation. So similarity preserving knowledge distillation guides the training of the student such that input pairs that produce similar or dissimilar activations in the teacher should do the same thing in the student. They should produce similar or dissimilar activations in the student. So similar input should produce similar representations. So here we go. So what do we have here? Let's try to take this particular block in the teacher model, and we want to match it to the corresponding block in the student model. So we have the activations here at the output from the teacher model, and we have the activations here from the student model. Now we need to try to match the activations, but it's not going to be possible to do that directly because they have a different shape. So what you want to do is you take the activations that you get from a bunch of data points. Let's say we have a mini batch of data points, which have, say, B data points. We take those activations and convert them into a similarity matrix. So the similarity matrix just tells us what is the similarity between the representations for between the data points in this batch. So we have a B by B matrix now. So the ij entry here tells us how the representation of I is similar to the representation of J. So we get the similarity matrix based on these activations of the teacher at this part of the network. And we similarly get the same similarity matrix based on the student representations. Now we are in the position to make distillation work because we have two objects here of the same dimensions. We have a B by B teacher similarity matrix, and we have a B by B times B student similarity matrix. And this is what we can use to do the distillation loss. So here we see a very different way of doing the distillation. It's not based on the representations themselves in terms of logits, but it's going to do the distillation based on similarities of these of the representations in terms of similarity matrices. So this is what we would like to match now. So just to say that in a little more detail, so this is the same picture that we had from the last slide. So what we have are activations from the student model and activations from the teacher model on the left and from the student model on the right. And you see that the dimensions are obviously going to be different. You have the representations for B data points, that's the same, but the other dimensions are going to be different in the student model and in the teacher model. So the first thing we can do is we can squash this kind of tensor into a matrix. So it's B times the rest of the dimensions have been squashed together, right? So we can do that. And now what you can do is you can use this matrix to compute another matrix, which is a square B times B matrix by taking the matrix times its transpose, and that gives us a B by B similarity matrix for the teacher. And doing the same thing with the student gives us a B by B similarity matrix for the student. And now we would like to match these two similarity matrices. And that's what we're going to do. There's an additional step here that just normalizes the entries in a particular way. So when you do similarities and so on, it usually is a good idea to normalize the similarities. For example, you might want all similarities to be between 0 and 1. So we do some standard normalization, and then we have two normalized similarity matrices. And then the loss can be, we can use a standard Frobenius norm to match two matrices. So we take the Frobenius norm between the two normalized similarity matrices between the teacher and the student, and this is going to be the distillation loss now. So you see that as in the original proposal, we have a distillation loss to match the teacher and student, but the difference is that the distillation loss here is based on similarities. It's not based on just the raw features. And the paper that we just showed you makes the case that in many applications you can gain this way of matching the teacher and student is very beneficial. So here is an example that is taken from that paper. So we have a very large teacher network, and we have a student network that we're going to use the distillation to train on. And what you can see is that the knowledge of the trained wide ResNet, which is a network with about 11 million parameters, is distilled into a much smaller student model, which contains only about 2 million parameters. So which is like a 5 times compression rate. And the accuracy loss is minimal. It's just about 0.3%. And this is just using off-the-shelf PyTorch without any specialized hardware or software. So just the benefit of doing distillation based on similarities. And these pictures show you the similarity information is indeed transferred. So this is an example of what we meant in the original title, that we are talking about many different avatars of knowledge distillation. So the knowledge distillation is a very basic concept about transferring knowledge, but it can be done in many different ways. And here is one way which is very different from the original proposal and is very effective when you use it in a very simple way without doing anything very special and so on. It's a very generic technique, and so it's a very powerful addition to the toolkit when you want to do efficient deep learning. And it's interesting that we are continuing to understand more and more about knowledge distillation. So this is a paper from last year's NeurIPS, just from December 23. So what exactly are we distilling? So what knowledge actually gets distilled? So this is a paper that tried to dig into this, and they come up with pretty interesting results, which show, for example, I've just flashed a few things, results that they discuss in the paper, that what you see as a benefit of knowledge distillation can be much wider than just looking at performance, just accuracy. So not only is it the accuracy that is maintained, but in the paper, they show that you can transfer many other beneficial properties of the teacher network to the student. For example, adversarial robustness. So it is robust to adversarial attacks. If the original teacher model has that property, that gets automatically transferred to the student without doing anything special. Invariance properties. So if there are properties that the original teacher network is invariant to certain perturbations or variations in the training data, then those invariance properties are also transferred directly to the student. And many transfer learning properties are maintained, are preserved for the student. So if the original teacher network, could be used in transfer learning, then the student network also is able to do that. So this idea of using distillation to transfer knowledge via representation learning or similarity learning, all of these. So in the paper, they examine many different ways of doing many of these different avatars of knowledge distillation, and they show that all of those avatars, they actually lead to the transfer of many other beneficial properties from the teacher to the student network. So the bottom line is that knowledge distillation is a very simple but extremely powerful idea. It's can be implemented in a very simple way and still get you very many benefits, not only that you preserve accuracy with much reduced cost, but also that you can transfer robustness, invariance, transfer learning properties from the teacher to the student. So now maybe we can illustrate some of these results, and I'll hand over to Willem to show you some more examples of how you can combine this with other methods in compressing neural networks.
Thank you, Devdutt. And like Devdutt mentioned, this next segment will be about how knowledge distillation synergizes with other compression methods and how, in combination, they can be used to create very efficient models for embedded hardware. So just as a recap, perhaps, what is model compression? Well, there's multiple different ways of compressing models. Two very popular families of compression methods include model pruning, where you identify and remove unimportant connections. This is highlighted here in the top figure, where certain connections in the model, highlighted in red here, are then removed in order to get a smaller model with fewer connections. And model quantization is the second technique, where we take the weights and the activations throughout the model and we represent them in the lower precision. So in this figure to the bottom here, we see floating values, in this case, just as an example, between 0 and 1, and how they can be compressed into integers, in this case, integer 8. So you would have values between 0 and 255. And these techniques, model pruning and quantization, what they have in common, right, with all compression techniques is that you start from a larger model and you go to a smaller model. And as we'll see, this is then very naturally combined with knowledge distillation, because we have an original model, which can be very large. We can then apply techniques such as pruning and then quantization to get a smaller model. And we then have a perfect setup to do this knowledge distillation. So we can actually have this original model and use that as a teacher model. So it's a powerful teacher model with very powerful representations. And we can then try to distill the knowledge of this teacher model to this compressed model in order to recover the accuracy, because these techniques, model pruning and quantization, they may come, if you do very aggressive pruning and quantization, they may come with a performance drop, an accuracy drop. And we can recover some of this with the help then of this distillation from this original model. And now we wish to illustrate this on two very interesting use cases. And we'll start by talking about how compressing vision transformers in these with these techniques can be used to accelerate the models on NVIDIA GPUs. So what we aim to show here is how knowledge distillation can be combined with quantization and pruning to compress vision transformers. And there's a very interesting paper that does just this recently that came out in CVPR 2023 called this Boost Vision Transformer with GPU-friendly sparsity and quantization. And what this paper does is they build quite a complex pipeline where they combine these three techniques. And basically what the figure to the right here illustrates, it's a very complex figure and we don't need to go into the details, is that you would have the original model, that is the top, like highlighted in red here, part of the diagram. And you would have a compressed, that is pruned and quantized model at the bottom here. And you would then combine the outputs and the intermediate features of these into various distillation losses. So you would try to have this floating point model. You would then try to distill all that knowledge to this compressed, pruned and quantized student model. And if we do this, we can actually get very powerful results, I would say. So here we see some results on a very common vision transformer in literature, which is the SVIN transformer. And we can see how this actually can have up to 4x speed up on certain NVIDIA GPUs. So here we see both server grade GPUs, that is NVIDIA A100, and embedded GPUs, that is the NVIDIA EDX Orin here. And we can see that for all these different SVIN architectures, there is a clear speed up with these techniques. And the speed up then is highlighted in this blue text here. So we see results for both the embedded GPU and the server GPU, how this can help. But of course, what we see here is all of these techniques combined. And what we're very interested in this presentation, right, is highlighting, well, what was the importance of knowledge distillation? Did knowledge distillation matter? And it turns out that, yes, it actually has a clear impact. So in the ablation study of this paper, we see here a table where they sweep various hyperparameters of this pipeline that we showed. And one of these parameters, just as an example, controls this feature-based distillation. That is the factor gamma here. So the third column in this matrix. What that value then shows is how much of the overall loss function will be this feature knowledge distillation. And obviously, if we put this to a value of 0, that would mean then that we have no feature-based knowledge distillation. And if we take a look at this row of when factor gamma is 0, we can see that the performance actually is quite low compared to the rows where the factor gamma is more than 0, right? So where it's 5, 10, or 2.5. And we see this in the next slide. So what we see here is, right, that for this row where factor gamma is 0, we have an accuracy, for example, of 82.2. And this is much lower, right, than when the factor gamma was, for example, 5, and it's 82.9. So the conclusion here is that, yes, knowledge distillation had a clear impact on these very good results. So this was an example of vision transformers for NVIDIA GPUs to show that this can also be used for other use cases. For example, accelerating mobile nets for ARM CPUs. We have this additional use case that we have prepared and done some experimentation on. So what we see here is the results of the original mobile net v2. So a floating point, no pruning, and no knowledge distillation. And we can see that it will have a 72% accuracy on the ImageNet dataset. So this is the original reported number from the paper, and it has a frames per second and of 5.5 on the ARM CPU. And 5.5 FPS, that would not be sufficient for many real-time applications. So we want to compress this, and we can actually compress this all the way so that we have 32 frames per second, which is sufficient for most real-time applications if we do pruning and a very aggressive pruning and quantization. But by doing very aggressive pruning and quantization, we see a drop in the accuracy. So we go from 72% accuracy down to 61%. And now, knowledge distillation can come to the rescue because we can use this original model. We can distill the knowledge to the compressed mobile net v2, and you can actually recover a significant portion of this well-performing original model. So we can jump from 61% from this very aggressively compressed model, and we can bump that up to 63. So now we actually recovered some of that performance. And this distilled model, it still has the benefits of the compressed model. It is the same kind of model architecture. It has the same pruning and quantization level. So it is still very fast on the hardware. It will have this 32 frames per second. So what we showed here was that knowledge distillation can be combined with these other compression techniques like model pruning and quantization. And if you want to learn more about that, or how we did this pruning and the quantization to actually get a 6 times faster model, then we would love to talk to you more if you want to learn more about this. And then you can contact us. And if you have any specific questions, you can also ask them in the chat here. And also another point, if you wish to learn more about the vision transformer compression, we actually had a separate presentation on this earlier. So if you want to learn more about compressing vision transformers, then I highly recommend you to check that out. But with that, I think I would like to conclude this presentation. And if you have any questions, the chat is open, and we would love to hear from you. Thank you very much.
Thanks a lot, Willem. So let's see what we have in the chat here. So there's a question about, it's a relevant question, says, what about the total training time? Isn't the total training time affected when you add knowledge distillation on top of the usual training pipeline?
Yeah, that's a very good question. So for the fine-tuning stage, that is the training of the student model, the training will be faster in the sense that it will learn quicker when you do this distillation, but it comes at the cost, right, of having to execute this larger model. And if you, in most research papers, it actually is quite a slow process when they do it. But there are many techniques you can use to accelerate it and actually get very much faster training with distillation. So this can include things like very efficient caching. And basically, you can view this execution of the teacher model as an inference problem, because you're no longer training the teacher model. So what you're really trying to do then is get very efficient inference execution. So with proper techniques and good techniques, you can actually get very quick total training time, faster than what the original training time was. It's a very good question. Thank you.
Okay, yeah, so it's great to know that actually it can be used quite efficiently in a standard training pipeline, and it will not disrupt usual training pipelines too much without and in fact give you large benefits. So it's a good idea to think about using knowledge distillation in your usual training pipeline. It's not going to make it too slow, and it's going to give you many additional benefits, such as what we discussed today. Okay, here's another question. So is it really true that you can use these knowledge distillations in any kind of deep learning model? I mean, is it really true that, or is there other places where maybe it's not such a good idea to do knowledge distillation?
Yeah, it's a very excellent question. One thing that comes to mind here is that there's something called the I think it's is it performance gap or representation gap, or if you try to distill a very, very large model down to a very, very small model, then the representations of those models are so different that you no longer get the benefits of knowledge distillation. So it is very important, actually, this model selection when you do knowledge distillation. It won't work well on just any model. So it is very important to select the right kind of student and teacher model pair. So that's a very good question. And finding this pair, this is something you can actually you can actually use these model optimization techniques for. So you can, like we showed here, you can do pruning and quantization to get a good student model. You can also do a neural architecture search. That is another technique that we didn't talk about here. That's also something you can use to generate these student models. So it won't work for just any model, and it's an important selection. This is how you select the teacher and student models. So very nice question.
Okay, yeah. So there's a good follow-up also, which is, let's say that you have a very large student teacher model, and we want to distill it down to a very small student model because we have very strict resource constraints. So there's no choice. We have to do this. We want to distill it to a very small student model. So we've heard some people say that you can do that by using, say, intermediate level teachers. So you can do the distillation not in one step directly to a student model, but maybe you can have additional steps in between where you distill to smaller and smaller models. Is that a good idea?
Yeah, yeah, perfect. It's a good clarification. So the problem I described, where if you have a very large model, it may be so different to the very, very small model that KD no longer makes sense. What Devdat described here is a perfectly reasonable thing to do, where you, instead of going directly from the very large model to the very small model, you actually take this process in multiple steps. So you distill to a slightly smaller model, and then you do that iteratively until you reach the smaller model. And this works fine.
Okay, another interesting question on this along the same lines, with a slightly different twist, is from Valentin Porot. He says, how well would it work? How well would it work if we use a VIT, Vision Transformer based teacher model, but then the student is a CNN based model? So what can you do that?
It's a very interesting question, and yes, and it can even have some benefits of doing that. There are some papers that have CNNs as the teacher model, and the student model are vision transformers. And especially in the early stages of training, it has been shown that the CNNs have this very powerful inductive bias, right? Where the representations learned they're very restricted. They have this inductive bias of locality and these what's it called, equivalent where equivariance, right? And this can actually have benefits. That's why CNNs work so well. But vision transformers, they do not have this inductive bias. And of course, that's a feature of vision transformers. They can learn much more powerful representations, but that also means that they will learn slower. So there are works that actually uses CNNs as teacher models and vision transformers as student models for the purpose of actually giving some of this inductive bias to the vision transformers. And especially in the early stages of training, this can help a lot. So yes, it can actually be a very good idea to mix and match these different architectures when doing knowledge distillation.
Yes, so in fact, it relates to the other paper we discussed in our webinar today, which is what knowledge is distilled. So you saw in that presentation, at least we hinted there, you can look at the paper for more details, is that you can get transfer of many other types of properties. And one of those is these invariance properties that Willem just mentioned. So if you have inductive bias of some kind, for maybe spatial inductive bias like in CNNs, that can automatically be transferred to this kind of knowledge distillation. So this is also another very powerful thing, right? So if you, in general, transformers, they're, as Willem said, one of the features is that they should be powerful, flexible, general, and so not have biases. But maybe if you have not enough training data, then maybe you would be nice to actually you transfer the inductive bias from a teacher model. And so this is another powerful feature of knowledge distillation, that such things, inductive bias, etc., from models which are well suited to the task, can be transferred automatically without doing anything very different and special. It transfers automatically through knowledge distillation in many cases. So that's another powerful thing about knowledge distillation to keep in mind. And good point that Valentin brought up in this discussion, and Willem answered. So here's another, of course, question that's, everybody is going to ask this question. What about LLMs? Can we use it with large language models? So, these are all the rage these days, right? So would knowledge distillation be useful with LLMs and in, say, for text, or now you can use transformers to do, text to vision, vision to text, all of those things. Would they be useful in those kinds of things?
Yeah, so like Devdat said, all the hype today is about LLMs, and the L in LLMs is large, so they are very large. So there is a lot of research on this, on distilling these very large models into something that can be more efficient, especially for inference and deployment. So there's certainly a lot of work on this, and there's actually some theoretic ground for why certain kinds of knowledge distillation works better in the context of language compared to vision. So, for example, the original formulation of distillation, where you just compare the output distributions, that can actually be very powerful in language, right? Because in language, you're really trying to model these probability distributions of many possible words, and there's a lot of context in these distributions, right? It's rarely the case that when you do next word prediction, there's a single. There's never only one possible word. It's always this the different possible next words. So, and this there's a lot of hidden knowledge in these distributions that the language models output, and you can actually make very good use of this for distillation. So it's a very, very hot field right now, both LLMs and compressing LLMs with knowledge distillation.
Okay, so then it brings up another question. I mean, we've seen that knowledge distillation can come in many different forms. You can have these output probability distributions, logits, you can use intermediate features, you can use similarities, and many other things you can do with knowledge distillation. So when you have, on the one hand, a suite of many different knowledge distillation methods, and on the other hand, you have many different types of tasks. I mean, you can have LLMs, or you can have text to vision, text to video, text to this, in many directions. So would it make sense to say that you would actually need to combine use different combinations of these different knowledge distillation methods when you train these things, and not just use one variant of knowledge distillation?
Yeah, no, definitely. And the paper with the vision transformer that we talked about today, they actually do combine all of these. So they have both this response-based on the output distillation, and they have this intermediate feature-based distillation. And the optimal model they find is one that combines both of these. So it does make a lot of sense to try to find the best combination.
Okay, so that then there's somebody here with the machine learning hat on. So when you say this, you're opening again the okay. Should we even learn this combination of different knowledge distillation? So
yeah, no, you're making a very intriguing suggestion. It would be very interesting if we can actually automatically learn this. Of course, there is some problems in making this differentiable, but it can certainly be viewed, as a hyperparameter problem, and you can explore that. And there's also, there's also some heuristics to it. Certain kinds of models there will be a lot of similarities between, what kind of distillation worked well for one model. If in another use case, if it's similar, it would probably be the same there. But it's a very interesting suggestion you make here, if I understand you correctly, Devdat, that maybe one could even make this differentiable and see it as a machine learning problem. I think that would be a very interesting direction for research to take. I'm not aware of any existing work that does exactly that.
Right. So now I think we are opening a can of worms for more research problems here. And so those of us in the audience who like to do research, that's probably very interesting. And those of those who are in the audience who want to have less complication and just do a very simple training pipeline, maybe they wouldn't want to get into learning combination of knowledge distillation. But it's an interesting topic. But the bottom line is that knowledge distillation is a very powerful tool, and it's an essential part of the toolkit for anybody working in this field of efficient deep learning. You can mix and match. You can combine it with many other things, as Willem demonstrated. It's very powerful in combination with pruning, quantization, and all of those. So you can add knowledge distillation on top of all those other things you're doing. One thing we haven't done yet, which we will have a future webinar on for sure, is a topic that Willem just mentioned, which is neural architecture search, right? That is finding the best architecture for a particular task without human intervention, but finding it automatically. And so this is a very big area, and so very natural topic for a webinar. But if you find the model using neural architecture search, again, you can add knowledge distillation in that context. So it can be very powerfully used in that context as well. So the bottom line summary for today is that knowledge distillation is a key part of the toolkit. Okay, now we got another question in when I was trying to sum up. So let's go with another question here. So are there many good software packages that you can use off the shelf to do knowledge distillation? So how well is this integrated in off the shelf tools that you can use?
Yeah, so for the most part, these techniques that we demonstrated today, they are available as part of, some of them are available as part of open source GitHub repositories for the papers. So this paper about vision transformer, knowledge distillation, it can have a GitHub repo, and there you have a distillation. But this is often then, it's hard coded for that particular use case. If you want a very general framework, so just finding this match of what to distill automatically and do that for any, custom model and a custom use case. There are very few libraries that does this. Of course, that's what we are about, Embeddle here. We create these software packages where all of these techniques, distillation included, and pruning and quantization, they can be applied efficiently for any model in any kind of training pipeline and for any kind of target hardware. So while this, if you want the cutting edge research, the GitHub repos, they do exist, but if you don't have time to clone every latest GitHub repo and some of them aren't available, then I highly recommend the kinds of software packages that we are building here at Embeddle.
Yeah, so we have to thank the listener for this question, because this again highlights one of the special features of Embeddle, that we offer this as integral part of our software development kit. So we have a number of different knowledge distillation methods available as part of our SDK, and those of you who are interested in that, you can of course contact us, and Willem would be very happy to tell you more about how knowledge distillation and these other techniques are integrated into our SDK, which is available for people who would like to work with us to use in their development pipelines. So maybe we can start winding down to the conclusion. So recap again. Knowledge distillation is a very powerful technique and very general and flexible technique, which is part of the basic toolkit of anybody doing model compression and efficient deep learning, and can be employed very effectively. So as Willem said, there are many papers out there with the repos that you can find it, but we also have a very unified offering of knowledge distillation in our SDK pipeline. And those of you who are interested, please contact us to know more. And of course, we're very happy to do pilot projects, etc., with you if you want to understand more about using those effectively in your pipelines and use cases. So thanks everybody for joining today, and keep tuned for future webinars coming up on many other topics. We mentioned neural architecture search. That for sure will be one of our future topics coming up. So thanks again, and see you for the next webinar.
Thank you. Bye.